It was only a coincidence that during one of the darkest periods in aviation history, Thunderstorm Research Phase 2 got off to a flying start. For the month of May 1947 also marked the beginning of the thunderstorm season in the area around Wright Field's all-weather flying center at Wilmington, Ohio. Setting up the research program to make flying safer through thunderstorm areas had required several months of preparation and coordination of equipment and personnel of the Air Force, U.S. Weather Bureau, Navy, and NACA. Although pilots have long known the dangers of tangling with Mother Nature's Mickey fins, no detailed and comprehensive data had been compiled on their structure and exact nature. So now plans had been formulated for investigative missions based on the few known factors and many hazards. From these flights utilizing the latest developments in instruments, recording devices, radio, and radar, it was ascertained that data and information might be secured and correlated for the formulation of scientific flying procedures in thunderstorm areas. The type of aircraft selected for these observations inside thunderstorms was the Black Widow Night Fighter, or P-61, with its low stalling speed of 105 miles per hour with wheels and flaps down, space to carry the necessary equipment and personnel, and its ability to withstand forces up to 6 Gs, or 6 times the pull of gravity. The Air Force had provided an adequate number of these P-61s, and each aircraft was equipped with special instruments furnished by the Air Force, Navy, NACA, and MIT for procuring aerial data from the storms and measuring the effect of turbulence and gusts on aircraft structure. Motion picture films recorded instrument readings and control signals registered during flight on an auxiliary instrument panel in the rear compartment. All such film records were to be analyzed to determine the disturbed attitudes of the plane resulting from turbulence and the magnitude of corrective control motions applied by the pilot. The measurement of turbulence being essential in formulating any rules and procedures for safe flying techniques. In each P-61, the crew was to be made up of an experienced instrument pilot, a weather observer, and an especially trained radar observer. All flying personnel had been carefully screened according to type plus experience, each one a volunteer for aerial experiences crowded with unknown factors and hazards. Airborne radar installations in each P-61 consisted of an SCR-720 receiver with a range of 80 miles and an APN-19 transmitter having a 100-mile range. This transmitter was designed to send out signals to the controller at the radar mission monitoring station, who could then identify and note the position of any aircraft and thus control the flight pattern by radio transmitted directions. All radar scope and photo panel data recorded on motion picture film during each mission was prepared for critical evaluation, often entailing a comparison of indications from several instruments photographed simultaneously. This phase of work at the start of the thunderstorm season soon developed into a tedious and exacting full-time job for many Weather Bureau specialists. Several types of aircraft, other than the P-61, had also been assigned and equipped for special purposes. One F-15 was to be used for photographing close-ups of thunderstorms and the making of complete reconnaissance flights around them at fixed intervals. The photographic equipment in this aircraft was a motion picture camera mounted in the nose section to be operated by the pilot. By tracing the path of this plane on each reconnaissance circle with radar, the exact location and dimension of the visible cloud could be obtained. Another type of aircraft, an AT-6, was to be used for snooping around and even penetrating some of the smaller thunderstorm clouds, particularly during the early stages of formation. In this installation, the photo recording setup utilized the standard instrument panel in the rear cockpit. The motion picture camera and lights for illuminating the instruments were turned on by the pilot. Before and after every mission, photographic installations on all aircraft were to be checked by a photo engineer for focus, lens setting, camera operation, film, and illumination. This frequent and thorough checking was necessary to ensure legible recordings photographed under turbulent flying conditions. To the huge Navy hangar at Minneapolis, another F-15 airplane was flown to be equipped with instruments to aid in the evaluation of flight hazards presented when lightning strikes an aircraft. Here, man-made lightning could be generated, aimed, and made to strike with a force equal to that of Mother Nature's product. A comparatively small generator, made up of hundreds of transformers for high ampere output, when hooked up with a massive one for producing high voltage, was capable of discharging crest voltages of 8 million volts and currents of 250,000 amperes. To record the magnitude and wave shape of high-tension discharges, man-made or natural, refinements of existing oscillographs were necessary. The large and very heavy type on the left could not be airborne, so one was developed that weighed only 30 pounds, including a built-in camera for recording all data presented on the surface of its scope. The entire assembly is enclosed in an airtight case 30 inches high, and the film loading arrangements are simple. Simple, too, was the equipment of Benjamin Franklin when compared to the potential sources of modern lightning research today. In utilizing the new lightweight oscillographs in the F-15 aircraft, 6 of these instruments were installed in the nose, each one connected by a heavily insulated cable leading to a part of the aircraft most likely to be struck with actual lightning. The nose, wingtips, tail fins, and canopy were the stations selected. One oscillograph had already been connected to the plexiglass canopy. Protection for the canopy against lightning was provided by a copper bar fastened to the plexiglass at the top, running from front to rear, and which served to pass currents to the outside surface of the aircraft. For lightning bolt tests aimed at the canopy, the generators were now turned on and set for a crest discharge of 4 million volts and 50,000 amperes. Shades of Ben Franklin. The canopy remains intact, and so do the nerves of the scientist in charge of the test, believe it or not. After the tests on the canopy, which proved the effectiveness of the method employed, lightning rods were installed at the stations on the aircraft selected as the most likely locations for lightning bolts to strike during flight. On the nose, on each tail fin, and at the tip of each wing. 5 contacts in addition to the copper bar protecting the canopy. With each of these points connected to the oscillographs installed in the nose section, the contact bristling aircraft was now ready for its nature-baiting mission. During flight, research procedures of the pilot, weather observer, and radar observer were to be closely coordinated with many ground-based weather, radio, and radar stations. Of the several radar installations of varying capacities and locations, the principal station was situated approximately north and 20 miles from the Clinton County base of operations. This powerful V-beam radar, the only one of its kind in use, and its personnel, were to control flight procedures of all Thunderstorm missions, as its massive and complex antennae scanned the sky for indications in 3 dimensions of all cold fronts, thunderstorms, and aircraft within a range of 200 miles. Meteorologists, Air Force pilots, and radar specialists, aside from the airborne crews, had been trained as a team in spotting the location, development, and travel of both storm and aircraft. Here the operators and controllers at many scopes could correlate their scope indications and plot the positions of all thunderstorm aircraft. This information, chalked up on transparent position boards, provided ringside seats for all operating personnel so that the exact location of each plane could be confirmed at all times. In order to obtain permanent records of scope indications, motion picture cameras affixed to several scopes were timed to operate at 4-second intervals, photographing the movement, development, and time of each storm and the position of all aircraft. This data to be compared later with the aerial information obtained by the P-61s. Range height indicators were used to provide a third dimension by measuring the height of thunderstorms from the ground. From indications resembling vertical spurts of flame, storms can be measured as high as 65,000 feet. To the trained observer, this plan position indicator reveals all the information necessary for controlling the movements of aircraft in the thunderstorm area, although at this moment a cold front is seen moving in. By means of such an advanced combination of radar and radio, thunderstorm research aloft can be controlled in any desired dimension. Radar and radio are also combined in the functioning of the GCA, or Ground Control Approach Unit, located close to the runways at the base of operations. In the event of closed-in weather for landing, the position of a returning aircraft can be seen and a safe landing procedure instituted. Within a range of 25 miles, this GCA can take over the vectoring of an aircraft from the V-beam station and channel in the plane with almost uncanny accuracy. The incoming aircraft's position, elevation, and drift are noted on scopes of varying ranges or stages, and then by using a predetermined channel of VHF radio, the pilot is talked in to a safe landing. Even with perfect weather conditions, all thunderstorm aircraft landings were to be made under the guidance of GCA. In using VHF as the primary means of communication, all channels during thunderstorm missions were designated for specific purposes. For air-to-ground and ground-to-air communication, a pilot was to be vectored through thunderstorms on Channel Fox, and for GCA landings, Channel George was to be used. With the latest developments in radar and radio so combined, flight procedures had incorporated every precaution for the safety of air crew and aircraft, barring, of course, those unpredictable hazards inside the churning structure of the thunderstorm itself. For securing the predictable factors of atmospheric conditions relative to thunderstorm research, the United States Weather Bureau had set up a micro-network of stations over a 350 square mile area just south of the base of operations. Of the 75 installations in this area, 63 were surface stations for recording the daily rainfall, temperature, humidity, atmospheric pressure, wind direction, and velocity at ground level. 7 radiosonde Raywin stations would procure the same data, excepting rainfall, at all altitudes by means of balloon-borne radio sondes. For data on the vertical structure of thunderstorms, 5 radar ray wind stations were equipped to track freely rising balloons with radar. From the movement of a balloon-borne target in 3 dimensions, the horizontal and vertical wind velocities could be determined. All Weather Bureau stations had been equipped with automatic recording instruments arranged in the most suitable combinations of Army, Navy, and civilian meteorological devices. For procuring data during a fixed period at low altitudes, this blimp-like device, dubbed a kite tune, is, as the name implies, a cross between a kite and a balloon. Its movement, while captivated, is a combination of flying like a kite and soaring like a balloon. The metal cylinder suspended by the kite tune encloses a thermometer connected to the captivating wire cable anchored on a reel. When this is paid out to a length of about 500 feet, instruments in the shelter record temperatures and wind directions at the varying altitudes of the kite tune. These records obtained at such intermediate elevations will be correlated with the data procured by other stations from high altitudes and ground level. For the ground level recording of atmospheric conditions, 63 surface stations like this one had been spaced at an average of 2 miles apart, each one equipped with wind and rain measuring devices, recording microbarographs, sensitive to minor pressure changes, and hygrothermographs, which utilize human hair, blonde preferred, no kidding, to determine relative humidity. Weather Bureau personnel had been assigned to maintain and service these installations for the duration of the thunderstorm season. All automatically recorded data was to be collected daily and each device checked and serviced. Each day's collection would include records of the previous 24 hours rainfall, surface wind direction and velocity, and changes in both temperature and humidity, all to be compared later with similar data procured at higher altitudes from other types of weather stations. Bordering the network area, 5 radar ray wind stations were located for the purpose of tracking balloon-borne targets through altitudes as high as the top of any thunderstorm and thus obtain horizontal and vertical wind velocities. The undersurfaces of this lightweight target were covered with metallic foil as the best possible surface for reflecting the projected radar beam. With the moment of release timed, the early part of the flight is tracked manually. When the balloon and target have reached an altitude favorable for automatic tracking, this device is switched on and the reflected radar impulses can be computed in terms of horizontal and vertical wind velocities. More comprehensive data from balloon-borne devices was to be procured by the 7 radio sonde installations distributed well within the area's network of weather stations. A parachute is included for this trip in search of information. This will aid in the recovery of the radio sonde, a device that sends out signals indicating relative humidity, pressure, and temperature. As demonstrated in the radar target release, this flight is also timed, as balloon, parachute, and radio sonde take off on their free flight to as high as the lower atmospheric pressures at high altitudes will permit, or to the bursting point of the slowly expanding balloon. These balloons usually burst when about 10 or 12 miles up. Here again, in order to compute wind direction, along with horizontal and vertical wind velocities, radar is used for tracking through the critical altitudes. The signals sent out by the soaring radio sonde are received by radio and recorded on a moving roll of paper. These signals, recorded at frequent intervals, indicate the degrees of relative humidity, pressure, and temperature at various altitudes and are noted on a condensed form for study and evaluation. Data of the flight procured by radar tracking is also transposed on a more comprehensive chart, and when combined with the radio sonde information, will present a complete picture of weather conditions on a certain date and during a specific period of time from this one particular station. In the Weather Bureau offices at the base, data from many daily reports, forms, and charts are combined. A parachute with radio sonde still attached is returned in a not too bad condition after having been recovered from a point several hundred miles away. Here, too, meteorologists at their plotting boards will transpose the figures of station-made observations to charts and graphs. In this manner, reports from all the 75 radio sonde, radar, and surface stations are correlated and reduced to a few simple graphs. These will present a comprehensive picture of all weather data obtained at the many stations within the local network and represent local weather conditions within the past few hours. As an aid in forecasting local weather in the weather section at the base, an actual picture of distant conditions is produced on a facsimile receiver every few hours. This device is similar to a wire photo receiver and provides a true copy of the current weather map and other data compiled at the point of transmission, which may be thousands of miles away. Also, the vast teletype network, which blankets the continental United States, constantly contributes information on weather conditions existing at thousands of weather stations and airports. These coded reports are made up chiefly of factors pertinent to surface analysis, of winds, temperatures, cloud types at various altitudes, and many other points of vital interest. Factors such as sudden and unforeseen changes in the movements or developments of cold fronts, squalls, and storms are noted on the weather map and will subsequently influence the decisions of the forecasting officer. Charts with indications relative to cold fronts and areas where thunderstorms are likely to build up are posted, and the information passed on to personnel active in the Thunderstorm Research Project. An auxiliary APQ-13 radar set installed in the weather section provides a means by which information on a chart can be compared with possible indications within the range of this particular installation. An auxiliary scope permits a closer study and broader interpretation of weather variables by more than a single forecaster or observer at a time. Discovering a cold front pushing in from the northwest means the probable building up of thunderheads in this area, and soon. Now, with all aircraft, radar, radio, and weather stations coordinated, let's inspect the flying personnel at close quarters. Men of a type plus experience selected for a now well-integrated procedure in hazardous research. Men alert, confident, careful, and eager. Air Force top instrument pilots, air-trained radar and weather observers with a total number of air hours that match the figures of a congressional appropriation. A lineup of guys that would please the most exacting of COs. Ground crews and maintenance men had been just as carefully selected for their ability to keep the P-61s in the best possible condition for such rugged missions as the penetration of thunderstorms.
how do you read? Over.
Roger, this is 356, reading you loud and clear, over.
Roger. 356, you're now clear to climb to 25,000 feet on vector 360, over.
Roger, this is 356, climbing to 25,000 feet, vector 360, over.
348, you're now clear to start your climb on 20,000 feet on vector 350.
Roger, this is 348, climbing to 20,000 feet, vector 340, over.
351, you're now clear to start your climb to 15,000 feet on vector 340, over.
Roger, this is 351, climbing to 15,000 on vector 340, over.
333, you're now clear to start your climb to 10,000 feet on vector 335, over. 51, you're now clear to start your climb to 6,000 feet on vector 345, over.
Roger, this is 335, climbing to 6,000 feet, vector 345, over.
356, you should be approaching the Thunderstorm now. Your assigned altitude, over.
Roger, this is 356, Thunderstorm dead ahead, approximately 30 seconds before entry, over.
Roger.
Penetrations were easily photographed by the F-15 aircraft. But when the Black Widows were being pushed around inside the thunderstorms, following them with a motion picture camera was photographically and tactically impossible. However, a clear picture of their attitudes and reactions to violent up and down drafts can be seen in a P-61's photo panel film made during one penetration. Note the disturbed attitude registered on the upper right instrument, while on the altimeter, lower right, rapid and extreme changes can be seen, bearing in mind, of course, that these indications were photographed at 1/6 their normal speed.
Triple three, you can now do a 180-degree turn and fly reciprocal. You're heading to re-enter the storm.
Roger, this is 333, turning 180 degrees to the left for storm entry, over.
How is the turbulence up there now, 356?
Roger, this is 356, turbulence moderate to heavy, precipitation heavy, over.
Roger. 333, you should be now entering the storm again, over.
Roger, this is 333, I'm entering the storm, turbulence very heavy, 2 lightning flashes to port side, precipitation heavy, some ice, over.
Roger. 356, you should now be entering the storm again, over.
Roger, 356, entry made 10 seconds ago, precipitation very heavy ice, over.
Roger. 348, your mission is complete. You can now start a vector towards base of 180, over.
Roger, this is 348, vectoring towards base of 180.
Roger. 356, you should be breaking out of the storm now.
Roger, this is 356, breaking out of storm into the clear, over.
Roger, 56, steer 180.
This is GCA 360, steer 220. You're coming in nicely, about left 2 degrees. You're 25 feet, too low, pull her up a wee bit. All right, you're on a runway and take over.
With 200 missions accomplished during the season starting in May and ending in September, it was also a coincidence that this month chronicled another achievement in automatic flight, likewise developed and initiated at this same Clinton County All-Weather Flying Center. All summer long, each mission had ended with the recovery of film magazines from each returning aircraft. Every all-important film record made during flight was properly identified for processing and analysis. 24-hour alerts, 7 days a week for 5 months, had resulted in 200 productive missions. Hundreds of thunderstorms of all sizes and stages of development were investigated, and 1,300 data-procuring penetrations accomplished through heavy rain, hail, snow, ice, and lightning. Motion picture film exposed in photo panel and radar scope cameras by the end of the thunderstorm season had assumed proportions of something more than a full-time job. A critical analysis and evaluation of 200,000 feet of flight instrument and radar scope indications will take many months to document. However, evaluated data procured by mechanical and scientific means alone is not sufficient, and only the human equation can provide the needed dimension in research. So immediately after landing, the crew of each P-61 was interrogated while reactions and observations were still fresh in their minds. A check on airspeed, attitudes, and flying characteristics of the aircraft was important, as was the pilot's interpretation of flight conditions and his reactions during turbulence. Notes by the radar observer on the progress of the storm through both radar and visual observations were compared with those of the pilot. And the weather observer's interpretation of cloud size and formation is integrated in each written report of the interrogator. Although any flight of aircraft through thunderstorms is potentially hazardous, these facts have been ascertained. With properly trained crews and adequately instrumented tactical aircraft, thunderstorms can be penetrated with safety. During these tests, several aircraft were damaged by lightning. Propellers were bent and noses pushed in by hail. However, no structural failures were incurred and no injury to air crews experienced. When the results of experience and research are documented, this project will have substantially aided in the making of today's hazards tomorrow's routine.